Okay, in this section, 4.5, we're going to talk about some special cases, the at least one, and then the conditional probability. We're getting into some harder topics, so please be careful. Maybe you need to rewatch this video a couple of times. And we need to make sure that we get ample amount of practice so that we don't repeat mistakes. Do not repeat mistakes. Once you made a mistake, stop and figure out why you made that mistake in your homework. If you're going through the lecture notes and you thought it's supposed to be calculated a different way, stop and think why and fix that. And the proverb actually goes along with that idea. Like a dog that returns to his vomit is a fool who returns to his folly or foolishness. Right? Don't be a fool. Do not repeat your mistakes. Learn from them, and it's better actually if you learn from other people's mistakes. Right? Okay, so let's take a look at these phrases. The first one was at least one. What does at least one mean? At least one means or is equivalent to one or more. Try to remember that. At least one is the same thing as one or more, right? One or more. The complement of getting at least one item of a particular type is that you get no items of that type, right? The complement is, and sometimes people think about complements and opposites as the same. It's not exactly the same, but the complement of at least one, or the complement of one or more, would be none, right? Think about this. One or more, if I choose just some kind of data set, one or more or none are complements. And so if you think about the way that we can write this symbolically, it would be probability of A would be probability of getting at least one. Then, using the complementary formula, probability of A is equal to 1 minus the probability that the complement of A is chosen, right? Which is none. So where probability of A complement is the probability of getting none of that type. We'll do some more exercises here to build some intuition. Well, here it is. Find the probability of getting at least one. Do you see that phrase? At least one? At least one head if you toss a coin 4 times. At least one head. So you could get, right, 2 heads. You can get 3 heads. That falls underneath the category of at least one. You can get all 4 of them to be heads, as long as one of them is a head, ends up being heads, right? And so we can do the formula one of several ways. We can actually find out what is the probability of getting 1 out of 4 coin tosses, 1 head. What is the probability of getting 2 heads, 3 heads, 4 heads, and then I'll add that all up. Or we can do this a shortcut way, recognizing that at least one and none are complements. Try to remember that. They actually rhyme in the English language, so that's perfect. The opposite of or the complement of at least one is none. At least one and none are complements. And so the way that we can find this probability would be if we find out what is the probability of getting no heads, right? Well, getting no heads means that there are all tails. Every single trial there'll be a tail. Well, then you ask yourself, well, let's find out what is the probability of getting no heads. All of them are going to be tails. What's the probability of the first being a tail? That's 50%. What's the probability of the second flip ending up a tail? 50%. Same thing for the third and same thing for the fourth. These are independent trials if you think about it, right? So I multiply 1 half by itself 4 times, you get 0.0625. And that is the probability of getting no heads. Now, since probability of getting no heads is the complement of getting at least 1 heads, I can use this formula right here. Probability of A is equal to 1 minus the probability of A complement, and say just subtract 0.0625 from 1, and you get 0.9375. Right? That is the probability of getting 1 or more heads, at least 1 head. And so that can be used to your advantage. Instead of calculating what's the probability of getting 1 heads or 2 heads or 3 heads or 4 heads, and adding up all of those probabilities, you can use at least one and none idea where they are complements to find out what that probability is. Okay, here's another one. If a couple wants to have 3 children, what is the probability of having at least one girl? Again, notice this phrase, at least one, right? Because you can think about this probability and find the probability the long way, or you can find the probability the shorter way, because you noticed this phrase, at least one. It's a special case. So you have 3 children, at least one is a girl. Well, you can have one being of the 3 being a girl and the other 2 are boys. You can also have the case where you have 2 girls and the third is a boy, or you can have the case where you have 3 girls, all 3 children are girls, and then you add the probabilities of each. Well, instead of doing it that way, why not find what is the probability of not getting at least one girl, right? What's the complement of at least one of the 3 is a girl? The complement of that is not getting at least one girl, which means that they're all boys. So what's the probability that they're all boys? Well, 1/2, 1/2, and 1/2 for each of the 3 children. When I multiply the numbers, and by the way, why am I multiplying? Because I want the first child to be a boy, for this case, and the second to be a boy, and the third to be a boy, to find out what is the probability that we do not get at least one girl. That's 1/8. And since at least one girl and not getting at least one girl are complements, I can just subtract 1/8 from 1 and I get 7/8. It's pretty likely that you will get at least one girl, right? Of 3 children, so you have 0.875 or 87.5%. So again, using the complement to your advantage instead of going about it the longer way. Here's some notation. Divide both sides by probability of A, and you get a formula for conditional probability. That's the second thing that we want to talk about in this section. So you guys remember this formula: probability of A and B is equal to probability of A times the probability of B given A. And this second one right here, when they are dependent, is the conditional probability. So what if we just solve for this by dividing both sides by probability of A? Well, then probability of B given that A has occurred is equal to probability of A and B happening divided by the probability of A happening. And please note that in this notation, probability of B given A is not the same as the probability of A given B, right? Because if you swap the order, you're asking a different question. Probability of B given A has occurred is not the same thing as probability that of A given B has occurred. Let's practice this with a contingency table. We remember the polygraph test, and now we want conditional probability. And there's a way to go about this that's pretty quick if you think about it. It says here, find the probability of picking a person for which the polygraph said that they lied. And here's the word that's key here for conditional probability. Given that they actually lied, right? Given. So let me go through the vocab words again. The word or, if that shows up, that is associated with the addition rule, right? The word and is associated with the multiplication rule. The at least one you should associate with the complement rule. And the word given here in this statement, you should associate with the conditional probability formula. Okay? Yeah, there's quite a bit now. 4 things that we need to keep in mind when we're reading these probability exercises. So there's a couple ways that you can go about this. I'll show you guys what I think would be the easier one. This word given, think about this. This word given, that they actually lied, is the first thing, right, that we're interested in. So this is going to happen first, given that they actually lied. And then what is the probability that for which the polygraph said that they lied? For which the polygraph said that they lied. Given that they actually lied. So the idea is that if they actually lied, that's this column right here. Did they actually lie? They did actually lie. And of these people, right, given that they actually lied, how many for which the polygraph said that they lied? Well, out of these two, 42 and 49, 42 of the people for which the polygraph said that they lied, right? So out of a total of, 51 people, 42 for which the polygraph said that they lied. You can go about that way. So the given, right? Given, everything after the word given is the row or the column that you should be focusing on. And the column total in this case would be 51. And then the first line for which the polygraph said that they lied would be the second thing. That would be your numerator, right? So for which the polygraph said that they lied, there's this row. And so the intersection between the row and this column would be 42. 42 divided by the column total would be 42 divided by 51. So you can go about that, or you can go about this a little bit more formula-wise, the way. Let's work through this step by step. Same exact exercise. It says here, if we assume that we selected a person that actually lied, then we are dealing only with 51 subjects in the second column. And that's what I was showing you guys right here, right? Given that we selected a person that has actually lied, well, how many subjects are those? 51 subjects, 51 people, right? So when we were reading through this, polygraph said that they lied. How many for which the polygraph said that they lied? 42 of the 51, right? 42 of the 51 for which the polygraph said that they lied. Now, again, you can go about this using a formula, probability of A and B. What's the probability that the person lied and the polygraph said that they lied? Well, A and B in a contingency table actually implies intersection. So they actually lied and the polygraph said that they lied. What's the intersection of that column and this row? The number 42, right? Or 42 out of a total of 98 people. You can think about it that way. That's the probability. Because in the numerator, it's probability, right? And giving you an answer of 42 implies that that's not a probability. Anything above 1 is not a probability, right? So how many people for which, out of all of these people, for how many people did we have people lie and the polygraph said that they lied? 42 out of 98. Okay. Well, the second one, what is the probability that you choose randomly a subject that lied? How many people lied? 51 people lied. And so if you think about this, the complex fraction here, the 98s will cancel if you flip and multiply. You can get 42 out of 51. Okay. Remember, let me actually do that. So we have 42 98s divided by 51 98s. Dividing one fraction by the other is the same thing as multiplying 42 98s by 98 51sts. In that case, the 98s will cancel. You can get 42 51st. I skipped that step in the notes. I think I didn't have enough room, so I want to show you guys that. You guys remember that we can flip and multiply like that when we divide two fractions. And why can we do that? Let me do one extra step here. When I do 42 divided by 98 divided by 51 by 98, and I'm going to do this. I'm going to multiply this complex fraction here by a quantity, and that quantity is going to be 1. Okay, so think about this. I'm going to choose a clever number to multiply by. Top and bottom, I'm going to multiply by the reciprocal of the denominator, right? So the reciprocal of the denominator is 98 51st. And if you think about it, what is this fraction equal to? 98 51st divided by 98 51st, that's just equal to 1, right? So it's like I'm taking the first fraction and multiplying it by a really weird form of 1. But here's the thing that we usually don't notice. What actually happens in the denominator is 98 divided by 98, 51 divided by 51. The denominator is equal to 1. Well, anything divided by 1 is itself. And the numerator is 42 98ths times 98 51st. So this right here shows you why we can flip and multiply. Multiply by the reciprocal of the denominator. So that just equals 42 98ths times 98 51st, or 42 51st, right? So that's a little bit of algebra review. Let's go back here. So we have our probability is 42 out of 51, 0.824. Here's maybe a second page to this. The total of the column and row that is described after the word given is the denominator of your probability. So the total of the statement after the word given is your denominator. So 42 plus 9 was 51. the intersection of the column and row that is described before the word given and after the word given is the numerator. So you have this polygraph said that they lied, given that they lied, right? Well, the denominator for that phrase would be the total of the column that they lied, right? That's 51. And then the numerator of my probability for this conditional probability would be the intersection of these two. Polygraph said that they lied, and they lied. What's the intersection? Polygraph said that they lied is this row. Actually lied is this column. The intersection of these two columns would be 42. That's the numerator. So that's another way that you can go about it. That would be a little bit more, conducive or a little bit helpful to you guys. Find the probability of picking a person who actually lied, given that we know that the polygraph said they didn't lie. Okay? So find the probability of picking a person who actually lied, given that we know that the polygraph said that they didn't lie. This is a little bit different, right? What's the probability of actually picking a person who actually lied? So actually lied here. What's the intersection of actually lied and polygraph said that they didn't lie? Polygraph said that they didn't lie would be 9. Right? The intersection of this column and this row is 9. That's the numerator. Right? And then everything after the word given, polygraph said that they didn't lie, which is 32 plus 9, or 41. That is the denominator of my probability. Again, or you can go about this the formula way. Find the probability of picking a person who actually lied, given that we know that the polygraph said that they didn't lie. So of the people, think about this, of the people for which the polygraph said that they didn't lie, how many are those? Polygraph said that they didn't lie. Of the people, 41 people. How many for which they actually lied? 9 of them. 9 out of 41. Again, I'm trying to rephrase it in different ways for you so that whichever one clicks with you, you'll be able to use that one with conditional probability. Okay. Again, you can use the formula. How many people actually lied here, right? So what's the intersection between A and B? Actually lied, and polygraph said that they didn't lie. 9 people of the 98. And then probability of A, what's the probability that polygraph said that they didn't lie? That's a total of 32 plus 9, 41 98ths. 41 98ths. Again, the 98ths will cancel, and you get your 9 41sts for that exercise. What is the probability of a couple having a girl, given that they will have 3 boys first? Okay. Probability of A having 3 boys. Probability of B having a girl. Right? And look at the word given. Do you see that? Again, conditional probability. And we can set this up in the following way. Again, probability that B having a girl, given having a girl, given that 3 boys have occurred. Well, what's the intersection of having 3 boys and a girl? That means you have 4 children. 3 of them are boys. What's the probability of getting a boy? 5.5, 50%. Probability of getting another boy, 50%. Probability of getting another boy, 50%. Probability of getting a girl for your fourth, child would be 50-50, right? So that would be probability of getting 3 boys and a girl. You just multiply 1/2 by itself. So the other thing would be the probability of getting A, which is having 3 boys. Probability of having 3 boys would just be 1/2 multiplied by itself 3 times. If you divide the two, 0.0625 by 0.125, you get 0.5 or 50% chance, which goes to show that obviously when there are independent events, right, having the 4th child being a girl is independent of having 3 boys first. And since there was this independence kind of lurking amidst this exercise, we actually didn't have to use conditional probability. We could have just asked, well, what's the probability of just having a girl? That would be 50-50, right? And so this probability that B given A was overcomplicated because we didn't realize that the two were independent. If we realized that the two were independent, we could have said, well, I don't even care about having 3 boys first. Probability of having a girl after having 3 boys is 50-50, irrespective of whether you have 3 boys first or not. Okay, hopefully that's helpful. Test for independence. If we do have probability of B given A, then the probability of B given A is equal to probability of B, then the occurrence of A has no effect on the probability of B. That is, A and B are independent events. And if probability of A and B is equal to probability of A times probability of B, again, the events A and B are independent events. You can associate that with replacement. So an example here, if A and B are independent, find the probability of A and B if probability of A is 0.3 and probability of B is 0.6. Well, if you're told that they're independent and you're looking for probability of A and B, you just need to multiply these two and get 0.18. 0.3 times 0.6, 6 times 3 is 18. Move the decimal over 2 places, you get 0.18. And that leads us to talk about counting rules in the next section. So take some time right now, maybe rewatch the video, and try several of the conditional probability exercises in section 4.5. Now please note that in the homework I put together homework 4.4 and 4.5 together because conditional probability and at least one and multiplication are more or less the same or revolve around the same multiplication, right? You're multiplying or dividing in one case or the other case. And so I've put the two homework sets together, 4.4 and 4.5. And if you need some help with those, of course, there's a separate video on the homework that I will go through for you guys. Hopefully this helps.